Okay, so we'll start with our design inputs and what are the requirement. Okay, what can be the specs. So if you see this slide, you can see that the process specifications like VT, K, COX, that's not in our hand. That's is how what the node technology we are using, and that depends upon that one. The process specification. Supply voltage will be given to us. Okay, what is the supply voltage and what is the range of the supply voltage, like plus or minus 10% of that supply range, or more or less. We have to design like that within that supply voltage range, our requirement should be maintained. And supply current, that also will calculate from the slew rate, or otherwise it will be given. And operating temperature and range, like we will do this one from minus 25 to plus 125, like that. Okay, or minus 42 plus 125. So that will be our operating range, and within that range our requirement should not vary much. Okay, so from this you can see that our requirement is gain, and this gain will mostly depend upon the channel length, and this gain bandwidth will be depend upon the width. Settling time, slew rate, settling time is our depends upon the tau, that is RC. Slew rate also depends upon our current, and our CC, that will be coupling capacitor, or we can say Miller capacitor. Common mode input range, that is for if our circuit is in common mode, how the what range our circuit will be operating, what will be the input range that our circuit can operate. Common mode rejection ratio, how much common signal our circuit, our op-amp can reject, how much power supply our op-amp can reject, that is power supply rejection ratio. Output voltage swing, how much swing is there, it should be equal to nearby the rail to rail, means VDD to BSS, but we'll see how much voltage swing is there. What is the output resistance, that is R2, or we can call it R06 parallel R07 from the previous slide. What is the offset, means for what voltage, if you give no voltage in the input, what is the output, that is the offset voltage, that much of voltage you have to provide. And this offset also depends on the gain, how much. If our gain is more, the offset will be less. If our gain is less, our offset will be more. Noise, okay. And layout area means how much area you have given, so that will be in the specification, the area specification, and within that area you have to do that, means the length and the width you cannot increase as you wish. So next slide, the topology output op-amp electrical design, how it is designed. So this is the topology we have seen. Here we have, here no current source is shown, so you can see M8 is not there at this point. So design of op-amp is depends upon the current and W by L ratio, component value, CR. Okay, so next, so experience is a great help, so that in that point I will help you with that one. Specification, that different topologies are there, like two stage will do now, there is a cascode, there is a folded cascode, and differential folded cascode with a class B push pull operation, class AB push pull operation. So there are some topologies, so do not try to invent new topology, because it will first start with the existing. If you need, just modify that one, that will help, otherwise it will take time. Consider the load and stability requirements. So previously, in the previous slides, we have seen that we have talked about that load capacitance and how much load that op-amp needs to take. According to that, we will design our circuit, and with that load also our stability requirements changes, and how we can stable that one we'll see. The Miller compensation, whatever we are doing is Miller compensation. If we do it in the folded cascade mode, that will be self-compensated approach. So for this video, we'll do the Miller compensation using our method. Okay, so design DC current device sizes proper for DC, AC, and transient performance, whatever given. So actually this should begins with the hand calculation, but here we'll use the GM by ID method and the simulation approach, which will save our time, because in as the length goes on decreasing, this hand calculation also goes on decreasing. So to get the idea of gain and bandwidth, what we'll do, we'll see that how much calculation is helpful and how much our simulation based calculation is helpful. Okay, compensation components also sized in this step 2 procedure. After each device sized by hand, the simulator is required to fine tune the design. It's good, and we'll calculate with the simulator, and we'll also fine tune that one with simulator. So fast cut is using hand calculation, and with our little bit of knowledge, we can use it with the simulator also. So we'll optimize and refine the optimization design. Okay. For planar circuits, planar MOSFETs, it is better to use the hand calculation, but because the channel length is going down and there are some secondary effects for that one, so we can use the hand calculation, but it will take much more time than the simulation based approach. So this slide we have gone through, that is a Miller compensation effect, how the Miller compensation does, and we see that how this Z1 and Z2 are affecting the compensation method in that OM design. So for this one, we'll go through the how the hand calculation approach is done, then we'll go through the simulation based. Okay, so this current is M5 and M7, and all the sizes is notation is SI and WI for W, and W means width, and L for length of the transistor. I is the number of the number of the transistors, like M1 and M2 are driver, M3 and M4 are load for those driver and current mirror, M5 is the current source, M7 is our output side current source, and M6 is your output side driver. CL is load capacitance, CC is your coupling capacitance or Miller capacitance, BTD, and BSS. So these are the notation. So for best performance in amplifier, it is always required all the transistors should be in saturation, and here we will go to the GM by add method to know the operating points of the transistors. Okay, M4 is the only transistor that cannot be forced into saturation, so this is important, because M4, the gate is not in our hand, the drain is not in our hand, so it is totally depend upon the M3 gate. M3 will be in a saturation, but how to make this M4 saturation, what we need to make this M4 VDS more than this VGS. Okay, VGS of BSG of M4. Okay, so you can first assume that VSG4 equal to VSG6. So VSG4, this one, equal to VSG6, we have to assume. This will cause a proper mirroring of M3 and M4. Okay, M3 and M4 can be proper mirror if this thing happens. Okay, because VSG6 is will be the VSD or VDS or VSD, you can say VSD4. So this voltage is VSD4. Okay, so if VSD4 equal to VSG4, then the M4 will be in saturation, and for that the VSG6 should be equal to VSG4. Okay, and M4 are same potential, so that M4 is guaranteed to be in saturation. Okay, so this VSD, So this is VSD, whether it is visible or not. Let me erase that one. Okay, so this voltage VSG6 is also VSD4. VSD4. So this VSD4, if VSD4 equal to VSG4, then M4 is in saturation. So if this VSD4 is VSG6, then we can say that M4 is in saturation. So this point, if this point is equal to this point, okay, because source is constant. If this point is equal to this point, then we can say M4 and M3 both are in saturation. So according to that, the current equation comes here. If both are in saturation, like M6, suppose VSG4 equal to VSG6, because VSG4 equal to VSD4, then VSG6, from that we can find the current, that I6 equal to S6 divided by S4, that is W by L of this one divided by W by L of this one, I4. Okay, and I7, you can see I7 current depends upon the S5, because how much current going through this one and how much current going through this one. Okay, so this is this equation I7, we can see that S7 by S5 equal into 2I4, because the current going through M5 is 2 times of I4. So for balancing, I6 should be equal to I7, and for that one this equation comes that S6 by S4, this part, is equal to 2 times of S7 by S5, called balance condition. So you can see, if your current, you are increasing it, like suppose here I'll go for multiplier. Suppose your X current is going through this one. Suppose X current is going through this one. Okay, and you are using a multiplier of 10 here, so 10x current will go through this one. Okay, and if your X is going through this one, 2x will go through this one. So in this part, 5x current, so it should be 5 times of that one, so 10x will be 10. So multiplier here will be 10, if, and the multiplier here will be 5. So whatever multiplier you will use here, half of that you will use here. Okay, so this is to satisfy M4 to be in saturation. So this is the calculation. We'll start with the slew rate. There are the two slew points. Okay, one is this output slew point and another one is this slew point. Slew points means those points where you see the capacitor and you need the current to charge this capacitance. Okay, so assuming that I7 is higher than the I5, so this current I5 is lesser than I7, so we can say that current here is more, while capacitance is because the smaller capacitance, this capacitance will be dominant, input capacitance will be dominant. Okay, let me name it 1 and 2. 1 will be dominant, and here the current will show the which so this these two, from these 2 points, this points one the one point, that is one number one, the pole side, this point will take more time to charge. So we'll consider the minimum of this slew rate. This one will be the minimum, means this will take more time to charge this capacitance. So we'll find the current at the input side, how much current. Okay, that should be our minimum, because that will decide our slew rate. So slew rate we'll do I5 by cc. Okay, I5 by cc, assuming whatever I have told, that CL is greater than cc, but with the gain cc will become more dominant. So first is gain, AV1 will be GM1 driver and the resistance. So GDS, we can say we can, okay, this formula you can see that minus GM1 into R0 R2 parallel R4. So this formula is this one, same as this one, because R0 to R2 is equal to 1 by GDS 2. Okay, so output conductance, this is GDS2, is equal to 1 by R2. So if you put this formula, you can get this formula, GM1 divided by GDS2 plus GDS4. So if you go through this one, this GDS2 is lambda. Okay, you can see it is lambda effect. So lambda ID. Okay, so lambda ID. So if you take this current, I5 is the current. Okay, so if you take this current I5, so lambda ID, so this I5 by 2, see this current in the both side. So current from this side is I5 by 2, this current is I5 by 2. So this I5 by 2, 2 is multiplied in the top side and 2 is GM1, and this is lambda 2 and lambda 4. Okay, that is the channel length variation. Okay, second stage gain is same. Okay, what is gain bandwidth? Gain bandwidth is our GM1 into CC. Okay, so you can see this is GM and this is the total resistance. And if you see this point, let me go to that slide. Okay, so this point is R1 by R1C1. This R1 is defined by 1 by GD, that is 1 by GDS1 plus 1 by GDS2 plus GDS4. And this C1 this C1 is dominated by CC. So from that, if you multiply, okay, from that, if this is the gain and this is your BW bandwidth, and this gain into this point, if you multiply, you will get a GM1 by CC. Okay, because this GDS, this resistance, output resistance of past stage will be that. Okay, so let me show that one. GM1 into R1. Okay, and this point is 1 by R1 and dominated by CC. So we are ignoring C1. So R1 cancel, it will be GM1 by CC. Okay, now output pole P2. Okay, so output pole P2, output pole is minus GM6 by CL. Okay, it will depend on the GM6 and CL. Okay, and your output RSP0 is right hand pole 0 is GM6 by CC. Okay, this is output MOSFET. Okay, for 60-degree margin, it requires that GM6 should be greater than equal to 2.2 times of GM2 CL by CC if all roots are above 10 GB in 10 GB. Okay, all other roots are outside that 10 GB, 10 times of gain bandwidth. Okay, from that they have calculated positive CMRR, negative CMRR. Okay, we can see this from in the GMIID calculation. Okay, so which point depends on which one? Minimum CMRR is depend on this one, maximum CMRR is depends on the VTH of this one. Okay, and this point is 0.2 time of CL minimum, maximum can be 0.5 of CL. For proper mirroring this point, this voltage VSG should be VST, and V out mean depends upon this one. Okay, V out max depend upon this one. Okay, means the saturation, so this needs to be saturated, this needs to be in saturation, so the VDS of this one should be VDS greater than or equal to VDS of this one to be in saturation, because these are in the current mirror stage. Okay, so again bandwidth depends upon the GM1, and that is how much faster circuit you can have. Okay, so these are the relation. From desired margin we can find that uh, we can find that this cc is greater than 0.22 cl, and also cc is less than 0.5 cl. Okay, 0.5 cl, otherwise it will be the opposite will happen, this will be dominant. Mm, Determine the minimum value of tail current from slew rate of the higher gain side stage, and we can find the S3 from calculation of this one. Okay, from that we can see that this value should be greater than 10 GB, means third pole that happens because of this point another pole will happen, this should be higher than the, means this should be in outside of the 10 GB, 10 into gain bandwidth product. From GM1 we'll calculate S2, and then this one, all this calculation will do. Okay, so this is theory. Before going through the GM by ID method, we need to understand these theories. Okay, otherwise there is we cannot understand what happens in the GM by ID. It is not a shortcut to anything. From this theory, this hand calculation, only GM by ID method you can understand and you can use it properly. Otherwise, it is useless. So here are the points. Okay, so you have to find that what is your range of UGB first thing, that is here, because of this one you can find the GM1, what is the minimum GM1 you require. Okay, if GM1 increases, your UGB increases, and GM1 increases if W1 increases or W2 increases. So if you W2 or W1 increases, the frequency that is increases. For gain you need to increase the L length. Okay, so what is the prior need we can do for that one. Okay, so let's go to the design specification and design something. Okay,